Okay, so we are working our way through the different rules, if you will, for finding derivatives of functions. We looked at higher order derivatives, and now we want to take a look at the derivatives of the trig functions. There's actually 6 trig functions, if you recall, and we're going to start with hopefully the most familiar one, the sine function. This is the graph of the sine function here. So let's just denote that as, we'll call it f of x is sine of x, right? And if you recall at 0, the sine is 0. It peaks at 1 where is that about? Looks like about 1.5 something. What is that? That's pi halves, if you remember. And then 0 again at, that looks like about 3.14 or pi. And then at -1, right, when we get to 3 pi over 2, and then by the time we get to 2 pi, which is about 6.28, we get back to 0. That's one complete cycle, the sine function, and it continues, right, repeats every 2 pi. What we're going to look at is trying now just to visualize the graph of the derivative of the function. Don't look below. You'll spoil the fun, right? To cover that up. Okay. What does the derivative of the sine function look like, first of all? So to do that, what we're going to do is we're going to sketch it. If you remember, given a function, sketching the derivative, what we looked at before is a starting point, if you will, is where is the derivative equal to 0? What does that mean? If the derivative is 0, that means the slope of the function is 0, which means the tangent line must be horizontal. Well, that's clearly going to occur at the local max and mins for the sine function. We have a local max, remember, at pi over 2. Sine of pi over 2 is equal to 1. And if I look at the tangent line right there, the bottom of the ruler, that line is horizontal. So I know the value of the derivative at that point is going to be 0. And that's going to be true at this minimum here, which occurs at 3 pi over 2. Right? There's a horizontal tangent line there, and so the derivative at that value is going to be 0. Same here. We'll go ahead and just plot these points that we know the derivative is going to be 0. Okay. So the question is, what's happening in between, say, these points where the derivative is 0? Well, anywhere between x was negative pi over 2 to positive pi over 2. Notice the graph of the sine function. At any point, what can you tell me about the slope of the tangent line, or about the derivative? Well, I hope you're saying it's positive, and that would be correct. If I take a look at any point, say I take a look right here, what's the tangent line at this point? Well, it would look just touching right. It's going to have a slope that's positive, right? And right here at this point, again, slope that's positive. Right over here, right, slope that's positive still. Right. Now notice right at negative pi over 2, the slope is 0. If x gets a little bit larger, then the slope becomes, right, some positive number. But initially, the slope, if we look at it, is pretty small, right? Like right here, at this point here, the slope of this line, the bottom of the ruler, we're going over 1, 2, 3, 4, 5, 6, maybe 6 or 7 before we go up 1. So the slope is 1/7 or 1/6, pretty small, right? But as we move along this curve, as x gets closer and closer to 0, what's happening to that tangent line? If we move over a little bit more, now our slope is steeper, right? So we go maybe over 5, and then go over 1, 2, and up 1. Well, not even that. Maybe over 1, up 1 almost. Right? So it's increasing. In fact, by the time we get to 0, what's the tangent line look like right there? If I just touch that, what is that slope right there about? Would you estimate? Right there's that's right there is about the tangent line. What it would look like right at x equals 0. For the sine function. Well, if I look at that line, I go over 1, up 1, over 1, up 1. So it's right at positive 1. So from here, we're about 1/6, 1/7, whatever. came up to, getting closer and closer to what? To 1. By the time we get in here, we're real close to 1. And then what happens? After that, as we move, as x goes from 0 to pi over 2, at different points on this graph, what's happening to the slope? It's still positive, but what's it doing? It's getting smaller. It's getting closer and closer to 0, right? And so we know right here the slope appears to be about 1. Let's put a plot at 1 when x is 0. So this is my derivative, right? The derivative of the function at 0 is positive 1. And so what are we saying is we move from this 0, right? The slope is 0 here. And we said what? As we move from negative pi over 2 to 0, the slope of the tangent line is positive, but it's small positive, increases up to 1. So it's going to increase up to 1 somehow, and then what happens after that? It's still positive, but it decreases back down to 0. So the graph looks something like that. Okay, and then in between these points, what would we say? Well, at any point here, what would the tangent line now have a slope of? Some negative number, right? So that's going to have a negative slope as we move left to right, right? In fact, right about here at pi, 3.14 about, right? The tangent line looks something like that. And what's the slope of that tangent line? We go down 1 over 1 about. It's about negative 1. So right there at pi, the value of the derivative is negative 1. And so what's happening? We start out here at pi over 2 where the slope is 0. A little bit more, say at 2, our slope is negative. And initially it's a small negative number, but it gets closer and closer to what? By the time we get right here to pi, the slope is negative 1. All right, and then what happens after pi, going from pi to 3 pi over 2? The slope of the tangent line is still negative, but what's happening is we move from left to right here. It's getting smaller. The slope getting smaller in absolute value, still negative, but getting closer and closer to 0. So what's happening then is the derivative is negative, right? Getting more and more negative till right at pi we're at a negative 1. And then what? It's still negative, but getting closer and closer back to 0 as we go through this segment here. And right now, because of the periodic nature of sine, I basically have a rough sketch for the entire derivative now, because this pattern is going to have to repeat, right? Because this is one complete cycle, if you will, pi units. And so this thing is going to continue on and look like this. Just repeating that pattern is going to continue. So when you look at that graph, what does the green curve that we've just drawn, what does this look like? This is the derivative, right? It's our estimate for the derivative of the function x. What does that look like? Well, if you didn't look and you guessed correctly, then give yourself a star, right? It is indeed the cosine function. The derivative of the sine function is the cosine function. Now we haven't proven this. I've sketched the graph and it certainly looks that way, but let me prove it with the limit definition now. The derivative of the sine function is the cosine function. So we're going to use, if you remember these trig limits we deduced using the squeeze theorem, we deduced this limit here. Limit as theta goes to 0 of sine theta over theta is 1. And then using this limit here, we were able to prove this limit as theta goes to 0, cosine theta minus 1 over 0 is 0. And of course, these are important limits that we use to evaluate sometimes some trig expressions involving limits, or limits involving trig expressions. So we're going to use these two, and we're also going to use a formula from trigonometry, the sum formula for the sine function. Do you remember this one? The sine of u plus v is sine of u cosine v plus cosine u sine of v. Okay, so I'm not going to derive this. Hopefully you did that when you took trigonometry. There's lots of relationships right between the various trig functions, and the sum formulas for the various trig functions are helpful, and they're certainly going to be helpful here. So if our function f of x is equal to sine of x, then what is our derivative going to be? Well, by the definition, remember, it's the limit as h goes to 0, f of x plus h minus f of x over h, right? There's our limit definition. So I'm just going to plug in to our function, f of x is sine of x. So what is f of x plus h? That's sine of x plus h minus f of x, which is just sine of x, all over h. So of course if I plug in h equals 0, I get the indeterminate form, 0 over 0. We've got some work to do. Now what is sine of x plus h? Is that sine of x plus sine of h? Just distribute that through? No. Right? This is not multiplication. This is not sine times x plus h. That would make no sense. This is sine of x plus h. You're plugging x plus h into the sine function. Well, I can rewrite this expression, though, using the sum formula for this sine function. So here u and v are correspondingly x and h. So using that, I can rewrite sine of x plus h as sine of x cosine of h plus cosine of x sine of h minus sine of x. Don't forget that, all over h. Now, how is this going to be helpful? Well, look at our limits that we have up above, our useful limits that we talked about. These two up here. Do you see one of those limits maybe in this? Somewhere kind of hidden? They're actually both in there. The one that sticks out to me is right here. Just, of course, we're talking about the variable changing here is h, right? Not theta, but same thing. This is like if I had h here, limit as h goes to 0, sine h over h. There it is essentially, but there's some other stuff attached with it. So I can't say that this ratio here, I can't say that what I've circled here equals 1 all of a sudden. Now I got this. No, you can't do that, because h is dividing these two terms as well. And in fact, the ratio sine h over h, if I just looked at that, or sine theta over theta, that ratio, again, remember, is never equal to 1. It is never equal to 1. But as theta goes to 0, it is approaching 1, right? That's the limit of that expression. So what I'm going to do is do a little manipulation and see if this makes sense. I want to take this piece here sort of out of the puzzle, but to do that I'm going to break up this big fraction into two fractions. So the first fraction will be this one I want over here. I'm going to put it over here. And then what's left up top, I've got the sine of x cosine h minus the sine of x. Of course, I have to put that over h, right? So I've just split it up. If I want to add these fractions, I can. I have the common denominator, combine the numerators, I get exactly what I have up there. Kind of rearranged the order I'm adding, but it's still valid. Okay. And then what I'm going to do is with each of these expressions, I'm just going to rewrite this one a little bit different. I'm going to take that cosine x out in front times what? The sine h over h. There I kind of got that piece that I need separated now. Okay. But I'm also going to show you the other one, because look up here. In the numerator here, notice now I have a common factor of sine of x. If I factor the sine of x out of this fraction, what's left up top? Cosine h minus what? 1 over h. Aha! Cosine h minus 1 over h. That's the other limit. Okay? So both of these limits pop up in this wonderful expression that we have to find the derivative of the sine function. Now, we have the limit of the sum of two functions. So that is the sum of the limits, provided what? Provided those limits exist. And then I have a product, right, in each case, and the limit of a product is the product of the limits, provided, again, the limit exists. And so let me just write all those limits out. This will be the limit as h goes to 0 of cosine x times the limit as h goes to 0 sine h over h, plus the limit as h goes to 0 of sine of x times the limit as h goes to 0 of cosine h minus 1 over h. All right. Well, what do we know about this limit? Should know what this is, right? That's our special limit. That's the one we talked about up here. It's equal to 1, right? What about this one here? Cosine h. Limit as h goes to 0, cosine h minus 1. That's 0. So both of these are 0. Now, do these limits over here, we know these limits exist. Do these limits exist? Well, look at these two. H is going to 0, but it's cosine x and sine of x. There is no h. So essentially, these are constants. And so the limit as h goes to 0 of cosine x is just cosine x. And the limit as h goes to 0 of sine of x is sine of x. So all these limits exist. We can do what we've done. And what does it tell us? What's this equal to? Well, cosine x. Oh, wait a minute. Where did this 0 come from? I said 1. I know I said 1. My hand is not obeying today. It's disobeying commands. Sorry. That is a 1, right? We said that limit was 1. I know I said it was 1. I just wrote it to 0. Sorry for the confusion. That's 1. So cosine x times 1 is cosine x, sine x times 0, 0. And so we're obviously left with cosine x, which is what we wanted to prove. And so now we have it. The derivative of the sine function is the cosine function, right? And you'll never have to go through this limit definition again. Well, actually you will have to go through something very similar to it, because what I would like you to do is, in the same way that I just proved the derivative of the sine of x is cosine x, I want you to prove that the derivative of the cosine function is -1 times the sine function. Now you could do it graphically as a startup if you want to. You can look at the graph of the cosine function and try and sketch its derivative and see if that looks like -1 times sine of x. By the way, what would negative sine of x look like compared to sine of x? Remember, if I just multiply the output by -1, that does a reflection in the x-axis. If you reflect, right, bring this part down and this part up for the sine function, you're going to get the graph of negative sine of x. -1 times sine of x. But if you do it graphically, that's fine. But what I want you to do is I want you to use this limit definition, very similar to what I have here, except you got to be careful. There's a sum formula for cosine, just like the sum formula for sine, but it is different. It is not the same as this. So cosine of u plus v is not this. Okay, it's different. So you need to look that up, and you can find that on the Trig help sheet that comes with the book, posted in Brightspace. And you can just Google cosine, sum formula for cosine, or addition formula, sometimes called, and you'll find it. But use that, and of course these two limits are going to appear. And I want you to prove that. I would like you to do that for homework. I'd like you to do that with your regular homework set as well. So that's an additional thing. You'll have 2 more additional things to do in this lecture. Okay. So 2 trig functions derivatives we have now. We need to do 4 more. The next one we're going to do is the tangent function. And I am not going to use the limit definition. And I don't want you to use the limit definition either, because we're going to use the quotient rule to find the derivative. And you say quotient rule? How do you mean quotient rule? Where's the quotient? If I take the derivative with respect to x of tangent of x, what am I going to do with that? There's no quotient. Well, I hope you know another important trig identity, the ratio identity for tangent. Tangent of x is equal to what? Sine of x divided by cosine of x. Right? That's a very important identity that we use quite a bit. Tangent x is sine of x divided by cosine of x. Now I have a quotient. Remember how that works? By the quotient rule. Right? So I'm going to make use of it right here. So it's the derivative of the top function, if you remember, times the bottom minus the top times the derivative of the bottom, all over the bottom function squared. So what is the derivative of sine of x? Well, we just spent a good bit of time proving that that is cosine of x. And what's the derivative of cosine of x? Well, you're going to spend a little bit of time proving that it's negative sine of x, right? That's what you're going to prove. And so what do we get from that? Cosine x times cosine x is cosine of x squared, or how do we usually write that? Cosine squared x. So I hope that's familiar to everyone, that cosine squared x is notation for cosine of x squared. So we take the cosine of x and then we square that result. That's what cosine squared x means. Minus what? Sine of x times a negative sine of x. Minus a negative is plus. Sine x times sine x is sine squared x. All over what? Well, cosine of x squared, we'll go ahead and write that as cosine squared x. Well, what can we do now? I hope there's one more trig identity that is just popping out at you like crazy right now. There should be a very important trig identity. Does anyone know what that trig identity is called? It begins with the letter P. You said the Pythagorean identity. You get a cookie. If you could spell Pythagorean, you get 2 cookies. I'm not even sure if I spelled that right. Pythagorean 1. Of course, you can prove that geometrically, knowing that the points on the unit circle are what? X comma y, or what? Cosine x comma sine of x, or cosine theta comma sine of theta, where theta is that central angle. At any rate, we get 1 divided by cosine squared x. There's our answer. That's not the way this is typically expressed, though. Again, this is a little frustrating maybe, but if we rewrite this as this, is this true? 1 divided by cosine squared x, is that 1 over cosine x squared? Yes, since 1 squared is 1, I get the same thing. But what is 1 divided by cosine x? That's another trig function. Do you remember which one? Secant. Secant and cosine are reciprocals of one another. And so we get our final result. Right? And so here's the rule that we have. We have the derivative of the tangent function. This is the way it's usually expressed, is the secant squared function. It's just the secant function squared. That's the derivative of the tangent function. And you will need to know that. Of course, you can derive it if you need that, just like I did here. In fact, what I would like you to do is, in a similar way, using the quotient rule, derive the derivative of the cotangent function. Derivative cotangent function is -1 times cosecant squared x. A little bit of a pattern to this. Now, cotangent x, how do you use the quotient rule? Well, tangent x is what? Sine x over cosine x. What's cotangent x? It's the reciprocal of tangent. So what? It's cosine x over sine x. So think about that, how that's going to play out. And you have a little bit of a work to do because there's a negative sign that needs to pop up somewhere. So make sure you do that one as well. I'd like you to do that for homework using the quotient rule, not the limit definition, but prove the cotangent function rule using the quotient rule. Okay, that gives us 4 trig functions. 2 more. So now we're going to find the derivative of secant using the quotient rule. And so how do we do that? Well, we just said secant x is the reciprocal of cosine. And so here's where the quotient rule comes in. The top function is just 1, which is going to make things easy. Derivative of the top times the bottom minus top times the derivative of the bottom. All over the bottom function, cosine x squared. I'll just write that as cosine squared x. Now, what's the derivative of 1, a constant? That's 0. So this whole thing is wiped out. 0 times cosine x is 0. Derivative of cosine of x, that's one you're going to prove, is negative sine of x. And so what do we get out of this? We get 0 minus a negative, or 0 plus sine of x. So I get sine of x divided by cosine squared x. Now there is indeed the derivative of the secant function. However, it's typically not written in that way. How is it typically written? Well, I'm going to break up this fraction into a product. Notice this is different than breaking up as a sum. If I'm doing a sum, I need a common denominator. If I'm doing a product, what do? We multiply numerators and we multiply denominators. So is this product the same as the original fraction? Yes. 1 times sine of x is sine of x, cosine x times cosine of x, cosine squared of x. But what is 1 divided by cosine x? That is secant x. What is sine x over cosine x? That is tangent x. And so there is the rule, the derivative with respect to x of secant x is secant x times tangent x. Very interesting. The derivative of the secant function is basically the secant function itself multiplied by tangent x. And that's the way it's usually expressed. And so this is equal to this, but it's typically written this way. And I do want you to be able to remember that, so you'll need to think about how, if you have to derive it. And similarly, I would like you to finally prove the last rule, which is the derivative of the cosecant function, which is what? 1 over sine of x. Do it similar to the way I did this one with the quotient rule, and show that its derivative is negative cosecant x, cotangent x. Okay? All right, 6 trig functions, 6 rules for derivatives. We found them all. So in the next video, we'll put them to use. We'll find some derivatives involving those, and we'll throw in the other rules that we know, like the power rule, quotient rule, product rule, constant multiple rule, etc., etc.